Hello everyone, my name is Joshua Sudduth, and today Daphne Unal, Logan Thurston, and myself will be discussing citric acid production via fermentation in Aspergillus niger. To begin, Daphne will speak about the background of the project and some alternative methods, and I will be discussing the selected methods and go more in depth about the process details. Then Logan Thurston will talk about the finances, safety, and external factors of the project.
Citric acid is a weak organic acid that can be found in many fruits. Its market has grown 5% in the past 5 years, and it's used in a wide variety of industries. The food and beverage industry represents the majority of citric acid usage worldwide, raking up over 60% of all purchases. As a flavor enhancer, citric acid adds refreshing tartness to most major soft drinks and is even used in high-end cooking. As a stabilizing agent, it is often used in the cheese-making process or to adjust the pH in brewing and winemaking. Approximately 30% of the citric acid purchased worldwide is utilized in the pharmaceutical industry. When it comes to medicine, citric acid is used to adjust the pH and help stabilize the chemical mixture. It is also used as an effervescent release agent, a chewable or syrup taste enhancer, and as a preservative. The remaining 10% of citric acid sales belong to a variety of industries, including household detergent and the cleaner production, cosmetics, adhesives, high-value polymers, and animal food production. The aim of this study is to design a citric acid production facility that produces 100 tons of citric acid per day, making up 2% of current citric acid market, and it is also desired to design a facility to be cost-effective. Sugar beet molasses was selected as a fermentation carbon source due to its widespread availability, low price, and low trace metal content. And the citric acid will be produced via fermentation of Aspergillus niger, and our method of fermenting will be submerged fermentation. The alternative method for citric acid production are surface culture and substrate fermentation. Surface culture is one of the earliest simple manufacturing methods. Surface culture is carried out in fermentation chambers and metal trays that are arranged on shelves. Also, A. niger is the most commonly used microorganism. It is collected over the surface of the medium in trays after inoculated at 30 to 40 degrees. In this process, the tray contents are kept to 1 to 2 weeks to ferment, and the spore germination occurs within 24 hours. This process is usually performed batch-wise with the substrate concentration around 160 grams per liter. The preferred raw materials are potato starch, beet molasses, or glucose syrup. Also, this method does not require high energy costs, therefore it is still used in many small production facilities. Despite being simple and inexpensive, we did not choose this method due to time and space requirement that makes the process undesirable for our large-scale applications. The second considered method was the solid-state fermentation. This method is the simplest method to produce citric acid, and it is similar to Japanese koji process to produce soy sauce. Solid-state fermentation is developed from microorganisms in low water activity environments, and they provide physical support and a nutrient source. In this method, the most suitable raw materials are fruit and agro-industrial waste, and especially cassava, because it provides the highest yield, which is 88 grams per kilogram dry matter. When the process is carried out with cassava, it should be fermented at 26 degrees for 120 hours. In solid-state fermentation, it is important to soak solid raw materials in water to moisturize the raw material around 70% depending on the absorptivity of the material. As in other processes, A. niger is a suitable organism because it does not require larger amounts of nitrogen and phosphorus. The advantages of this process are low cost and low usage of harmful chemicals. Also, in the other methods, trace elements like magnesium, zinc, manganese, calcium, and iron affect the process harmfully. Unfortunately, this method is not practical for our purposes because there is not much information available on a large-scale industrial applications. There were some alternative raw materials besides the sugar beet molasses. Sugarcane bagasse is a widely available and inexpensive material due to its natural fibrous texture. Even though it's a common raw material, we didn't choose it because it's not perfectly suitable due to the process method we choose. Another substrate we've been considering was the tubercles because it is inexpensive raw material too. But the tubercles are not commonly used raw materials for citric acid production because it tends to produce lower yields and lack of available literature about the applications to produce citric acid. So we did not choose this raw material. The last raw material we considered was the agro-industrial waste because it's a suitable raw material for solid-state fermentation. Some example of agro-industrial waste is apple pomace, pineapple waste, banana peel, and kiwi fruit peel. This raw material is inexpensive, but it is not available in stores and should be produced directly from farmers. We decided to work the process with submerged fermentation, so we eliminated this raw material too.
To begin our process, our raw purchased substrate will be passed through a primary filter, which will remove any large biological debris from our molasses. Next, the mother liquor is sent through an ion exchange column, where it will be treated to an appropriate concentration of trace metals and other ions. The mother liquor is then treated with a heat exchanger to sterilize the substrate. Ammonium sulfate, minor salts, and water are mixed into the solution to fix pH and ensure necessary conditions before putting it in the fermenter. Fermentation is done on the substrate via Aspergillus niger in a submerged fermentation tank. This occurs in a large fermenter that is roughly 950 meters cubed in volume. Filtered air is passed through the tank to supply oxygen to the fungus. The tank is stirred mechanically for about 7 days before being transferred to the press filter. Here, the desirable products of A. niger's fermentation are separated from the fungal mycelium itself. Milk lime is then added to the filtered solution to precipitate calcium citrate in the form of tricalcium citrate. This calcium citrate is filtered from the mother liquor. The remaining slurry is sold as an animal feedstock. Sulfuric acid is added to the calcium citrate to form gypsum and citric acid. The gypsum is removed from the aqueous citric acid and is sold as a valuable byproduct in our project. Next, crystallization occurs. In this step, the dissolved solute is turned into a solid crystal containing 7 weight % water. The water and solid crystal are passed through a filter to return the solidified citric acid. Finally, 97% of the water is removed with drying at 110 degrees Celsius to achieve our final product of 99.8% pure anhydrous citric acid. The stoichiometries for these processes are shown below. The left shows the fermentation process, the middle shows product precipitation, and the right shows gypsum formation. Here we see a more detailed diagram of the process. This shows how our inputs, indicated as diamonds, are converted into outputs, indicated as squares. The letter S followed by numbers indicate a stream connecting two processing units. Pumps between streams are indicated as a circle between two arrows. Storage tanks are used throughout the process to allow control of when certain process steps are being used. In this diagram, we see how air is compressed and filtered before entering the fermentation tank. After exiting the tank, the air is filtered again before being vented away from the process. Citric acid is mainly produced in China. Here, 60% of global product is made, while only 12% of global citric acid is consumed there. 50% of global citric acid production is consumed in places like North America and Western Europe. The remaining roughly 40% is distributed in the remaining countries. 60% of total global citric acid is utilized in the food and beverage industry. Here, it is mainly used as a flavor enhancer, stabilizing agent, or as a food preservative. 30% is utilized in the pharmaceutical industry for use in stabilizing and adjusting the pH of medicines. The remaining 10% is utilized in various industries for things like detergents, cosmetics, and adhesives. The total market revenue for citric acid is expected to increase 30% in the next 4 years. This increase is due to the demand for things like digestive medicine in the pharmaceutical industry increasing, and the demand for food additives in the food and beverage industry increasing. Gypsum is another byproduct of our project that has value in various construction industries. Our process makes up about 4% of the global gypsum production. The market revenue of gypsum is also expected to increase at a compounded annual growth rate of 10%. This increase comes as the demand for construction material increases. Beet molasses is our raw substrate used in citric acid production. Beet molasses is used in roughly 60% of all sugar production in the United States. The price of beet molasses is expected to increase 1.9% in the next 10 years.
I'd like to now talk a little bit about the financial side of our project, and I'll start with capital costs and investments. The capital cost calculations were performed in CapCost software and Microsoft Excel, and we had some unique equipment that had to be entered manually into CapCost. For example, we had some extremely large microfilters that filter the air that is sparged into our fermenters, and CapCost didn't like how large these filters are, so we had to scale their cost based on similar Super Pro equipment, and we scaled based on time and capacity. And then in the bottom table there, you can see our capital cost metrics. Our plant bare module cost is about $16 million. Our plant total module cost is about $18 million, and our total grassroots cost is about $20 million. And then to summarize our investments, those occurred between years 0 and 2. A $10 million land investment was invested, as well as a fixed capital investment sub-land, and that was split between years 1 and 2, 60% in year 1, 40% in year 2. And then a $15 million working capital investment was invested at the end of year 2. Next, I'll talk a little bit about the costs of manufacturing of our plant. These calculations were performed in CapCost as well, and we had to make a few key assumptions. The first of these assumptions was that our waste streams, at least on a financial basis, could be considered to be wastewater, and that's because each of our waste streams is primarily composed of wastewater, and none of them have any highly dangerous or toxic chemicals in them, so we figured the cost would be about the same as treating wastewater. The second assumption that we made is that our unique equipment, that same equipment that was described in the previous slide, that the cost of manufacturing of that equipment could be scaled based on time and capacity, just like before from Super Pro, and we did that. And then our final assumption was that the cost of mixing in some of our mixing steps is negligible, and that was based on the amount of time that it takes to mix. Most of our mixing steps are between 0 and 2 hours in duration, and each batch of our process is about 8 days, so it's a negligible amount of time. And you can see our results. Our raw materials cost was $24 million. Our annual utilities cost was about $3.5 million. Our annual operating labor is about $1.5 million. Our waste treatment annually costs only about $142,000, and our COM-D came out to about $41 or $42 million. So profitability is where the rubber kind of meets the road on these projects, and we assessed the profitability of our project using the spreadsheet method that Dr. Phil Russell gave to us in class, and we assumed that our project lifetime would be 20 years, a 2-year startup, and then 18 years of production. We chose a 7-year MACRS depreciation schedule and a 21% tax rate, as well as an 8% discount rate. Now, the previous slide showed the spreadsheet that was used to perform these calculations, but our results are as follows. Our payback period was 3.52 years. Our cumulative cash position came out to be $187 million. Our cumulative cash ratio is 5.31, and our rate of return on investment is 100.3%. Now, when it came to our discounted profitability metrics, our discounted payback period is 4.9 years. Our net present value was $58 million. Our present value ratio is 2.47. Productivity is 1.47, and our discounted cash flow rate of return is 22%. In summary, we are seeking to make 100 tons of citric acid per day. Our target markets will be the food, beverage, and pharmaceutical industries. Submerged fermentation of sugar beet molasses using Aspergillus niger will be our method of choice. We will pre-treat the sugar beet molasses, ferment it, isolate the resulting citric acid, and purify it before selling. We plan on taking advantage of a growing market and thus having a high likelihood of immense profitability. We also have a fair number of conclusions that are small and technical, but the largest conclusion that I want to point out is we have concluded to proceed with our facility build and eventual startup due to our high likelihood of profitability. Ensuring the safety of plant workers as well as the general public surrounding the plant is by far and away our number one priority in this entire process. I won't go through this entire safety chart here, but I do want to touch on what is written in red, which is our worst case scenario for our process. And the worst case scenario that could potentially happen in this process is fermenter overheat and explosion. And this would happen from the unlikely event of extreme fermentative heat buildup in one or more of the fermenters, and that could cause spontaneous combustion of the contents of one of the fermenters, leading to a pressure buildup and a potential explosion. So the way that we propose to keep this from happening is to install emergency cooling water supply and pressure relief valves on each of the fermenters. I would like to conclude our presentation by discussing some environmental and societal considerations. The first of these is carbon emissions. Now, there will be some carbon derivatives coming from our fermenters, but it is necessary to remember that any carbon that comes out of sugar beet plants was already fixed by sugar beet plants through photosynthesis. So that area is not concerning environmentally, but the concerning part of our process is the transport of materials and products to and from our facility. Now, traditionally, this would involve the combustion of fossil fuels, and that seems somewhat unavoidable right now, but we are open to looking into more sustainable methods of transport moving forward. As stated previously, the waste streams from our facility will all be treated prior to release, and that will just ensure public safety. And societally, our plant will create a lot of jobs. We will employ 50 to 100 new workers, and that will boost the economy of the area that we put the plant in. But the large industrial buildings may not necessarily be easy on the eyes in the opinions of some, and there may be a fermentative smell coming from our fermenters. So it is necessary to look into placing this plant in a rural area. And with that, I would like to conclude. Please reach out if you have any questions for us, and thank you for listening.